Hello everyone. We'll look if everything works properly. It seems so. Okay, perfect. Do I have the okay? Um, okay, perfect. So everything seems to work. So first of all, thank you all of being with us tonight. My name is Andrew. First, I will introduce myself. So my name is Andrew. I'm currently a student to complete my master degree in computer science engineering. I have a wonderful life partner, three kids, and a cat too. And before starting my master degree, I worked 2 years in industrial software development, stuff like Endon, C Sharp, and usually in the Windows environments. And after that, I was like uh, sucked into the world of web development. This was what was available in that time. So I worked for almost a decade in that area. Did a lot of DevOps, was more a back end than a full stack or front end. I'm not a fan of JavaScript, sorry. And at some point, I got bored, not because it was not interesting, but because from the start of my young career, and when I was at college, I was more interested in low levels such as C. Assembly was something that was very interesting for me, but also how the computer works, how the CPU works, how the GPU works. So um, uh, the it, it was missing from my experience I had during my career. So one day in 2016, I went into the engineer faculty in my hometown, and then I saw electric motorcycle, I saw drones, I saw PCBs, and I was hooked. I said I need to go back to school and try to figure this all out, and I did. So fast forward uh, today, I completed my baccalaureate. Sorry for my French English. I speak mostly French, so it might happen sometimes that I will speak some word you might not really understand. Sorry about that. Okay. Um, so I did a lot of during my back. I, um, I did a lot of stuff such as AI, robotics, and but every time I work on those fields, I was always um, um, like I don't know how to say it, but what was really important for me was all the compute parts. So, for instance, a Raspberry Pi or Turing Pi microcontrollers for robotics, Jetson that can be used in robotics too, but can bring AI to the edge, what we call, and FPGA, what we will use today and see what is all about. You might never have heard of an FPGA before, and one of my goals with this channel on Twitch is to first teach you what it is, how to use it, but also for me to go deeper into that technology, since I don't have any corporate experience with FPGAs, only in the context of my baccalaureate and my master. So I also did during my master degree. So to be I don't know if I'm in Canada, so I don't know if you know, but there's two type of master degrees. There is a research one and a class or course one. At first, I started with a research one for almost 2 years, 2.5 years, and I was in partner with a company, but unfortunately that partnership didn't work out. So it's basically 6 months that was lost and wasn't of any value for my master. And it was near the COVID, so it was difficult to work with other people. All the dynamics we have at the baccalaureate, um, uh, when with all the people and the discussion and all of that wasn't there. So I had to make some changes. So right now, my master is a course one, and I took PCB design. So that was very interesting. I also took quantum mechanics for engineering. That was a very difficult course, very math heavy, but so interesting. Again, like I said earlier, I'm very interested in all types of compute modules. So may it be a CPU, a GPU, but it could be a quantum computer, it can be a FPGA like we will see today. It could be other stuff like I can show you other interesting thing that exists. So for instance, oops, not that here. There's a company, and for all intent purposes, there is no company I will display today, either AMD with the technology I use right now, or other company that I will display. I have no relation with them, so it's there is no sponsorship of any kind, and if it ever happens, you will be notified. So here, whoops. Here we have light matters. So it's a compute chip that will use lights as opposed to electricity in the chip, and for less energy it can do a lot of computation. The computation it does, it's similar to what a GPU does. So it's very close to a not close, sorry. It's a lot about multiply and accumulate. This is some in engineering, in either in video games or in AI, or almost everything you do with a GPU or whatever. It will use the basic compute block will do a multiply and accumulate. So it multiplies and add to a register. I can explain it better later in the stream. So light matter does that. There is other company that use lights in different ways. If you're interested, there's a great channel in YouTube. It's let me get it here. Right. Oh, wait a second. Sorry about that. Okay, so I will go in. You don't see. Okay, so it seems that you don't see the stream. But wait a second. Do we have technical difficulties? Not here. Sorry about that. Do here. This one. That's weird. Are you sure you don't see? Because I see on the Twitch stream manager. Yes, it's okay. Okay, okay. Perfect. Just a second, I will. Okay, sorry about that. So the channel I'm talking about is Anastasian Tech right here. So just a second, there is a problem. This one. Okay, perfect. Perfect. So on our channel, there's a lot of information about new technology that is used in computing, and there were a photonic chip that was presented 2 weeks ago that was very interesting. For what I understood, is it uses different wavelength of color for to transfer data at the same time, instead of just what Lightsaber does is send only one wavelength of color. So again, don't quote me on this. I don't know all the technicalities behind those technologies, but Anastasian Tech is very good to explaining all of this. Perfect. Okay, so other things that can be interesting is a neuromorphic computation, but not there is some technology that uses the term neuromorphic, but what I'm talking about is more akin of how the brain cells works. So when we use our 7 or 8 brain cells we have, it's not like how AI works nowadays. Current AI, it's again a multiply and accumulate, so it's neurons, and those neurons have a value. So for example, to simplicity, the value could be for example 10, and either we have a lot of neurons, so the one with 10, one with 3, one with 4, and we pass the input value we have. So for instance, let's say we have a cat and the first pixel is blue, so the value of blue, for instance, is and I say the value I say are not relevant here, but let's say the value for blue is 17. Okay, so the 17 will go through all those neurons and be multiplied and added, so at the end there will be a value, a response, if you will. But this is not the way as a brain cell works. A brain cell works in its frequency. So there is a electric discharge. I don't remember the name of this phenomenon, but I will show you. Just a second. I will connect this here. Like so. It won't be long, sorry about that. Okay, perfect. Oh. Allow. Okay, it's coming. Can you tell me if everything is okay with the sound yet? Okay, perfect. Sorry about that. So if I go back here, it's loading. Oh yeah, I have to start here. Start like that. Perfect. Okay. So how the neuron works is, so whoops. There is the neuron, and there's another neuron here, like so, and there can be other dendrites here with another neuron here. Okay, so there's a neuron that sends a signal over there. Sorry, just a second. Oh. All right. Okay. So, what's happening is this will trigger, will send a signal over here from another neuron, or it can be, for instance, a nerve or neurons, in fact. But let's say a nerve is excited. It can be eat like neuron, a nerve, or it could be a pressure one, whatever. So this will send a signal, and at some point, this neuron will ignore, or because it won't have enough. How can I say that? It will not have get enough sensory information to say, hey, it burns, something like that. Okay, but at some point, if I do a graph, at some point, this here will produce some electricity, and at some point, it will trigger a discharge on that one that will propagate along this part of the brain cell. When it does, it will do the same thing for this neuron and this neuron. One of those neurons will be more sensitive than the other, okay? Or sometimes the one neuron could be, for instance, the connection could be recessive, so more stimuli will attenuate other signals, and other could be additive. So if there is multiple signals coming, it will add to this part of the signaling. All right, but all of this system, and you can imagine there's another neuron here and another brain cell here, and all of those are like added together, but will trigger signals that will be in around maximum 1 kilohertz. All right. So this is how everything goes through the brain. It's a very simple oversimplification, and there are currently people who's working on memory star. Okay, so those electronical devices, they are very difficult to do because they are very sensible to temperature, and considering that using electricity in a circuit will produce heat, it is very difficult for now to have very reliable resistors. But if we can crack this technology, we will get to a point where we will be able to simulate how the brains work electronically. So maybe you're asking, why would we want to use a brain-like structure to do computation? Someone could argue that, for instance, the brain, like the best mathematicals people, don't compute as fast as a computer. Yeah, in parts, but one of the main power of the brain is, first, it uses about 20 watts of electricity, and second, it can do a lot of multitasking in the same time. Some stuff that it's very hard to do, for instance, walking, talking, and looking and recognizing someone or an object in a scene, for instance. So I don't remember all the numbers, how fast someone usually is able to recognize someone, but I'm pretty sure it's around 100 milliseconds. And to do the same thing using conventional electricity, it's way more consuming than that. So that's one of the part. I know one technology that is kind of using stuff similar to that. I don't remember the name, so I'm sorry. If I get it later, I will get it out for you. But I think it's Intel that made like a thumbstick. So if I found it, or if you know it, just post in the chat. Okay, and of course there are companies that do our quantum computing. Why is not working? Perfect. Okay, so here is D-Wave. One of it's a Canadian company. I think they are in British Columbia. If I'm correct, this computer, one of the you have to know is that there is like two type of quantum computer, for what I understand. This one is similar to, for instance, if I take in electrical computing, there is an analog computer. So D-Wave is making a analog quantum computer compared to IBM, which does a more like a gated or a digital quantum computer. Again, it's very oversimplifying. I don't want to just deep dive into those technologies, but those are technologies that are very interesting to me, and that will probably gain traction with time. Okay, so this is the well, it's a summit, but this is I think it's like 1,000 gate quantum gate into that big big machine. What is interesting also with quantum computing is that the quantum computer doesn't do much about like going to the internet or word processing or data analysis. It's more it needs computers to work alongside it. So that's why you see a lot of other rack around, and it's pretty much the same thing with D-Wave. There are needs, and there is computers, digital computers around. All right. So that's pretty much what we will talk about here for different type of computes. And so, like I said, I took a quantum computer. That it's not a computer. It's a quantum course for engineering. So it was very math heavy, and at the end we saw a little about gates and stuff. It was really a surface class. It was made for I don't remember the term, but people that are at master's degrees or doctorate. So it was very interesting. So other thing I did was and that is in relation to what I said earlier with the neuromorphic design. It's a class on neuromorphic computation. So we use a library called Brian, and so I think it's not that one. The name is Brian, so it's very hard to find on the internet, and it's been a while since I worked with it. So it was a Python library. Okay, yes, I think it's that one. Is there a wiki, something? Okay, so sorry about that. I think there were something more interesting than that. Let me look. So this Brian 2, yeah, it was the second version. So it's a library in Python that we can define network of neurons, and it will be simulated. For those of you who already did AI, probably did AI will probably know is that there is a very easy, how can I say, very entry level type of exercise we do. It's called MNIST. Back in the days, it was the big stuff, but nowadays you can do that kind of stuff with neurons in about conventional, I mean, network, AI network, ML network, and you can use like a 4060, and it will be done in about 2 or 3 hours max. I don't know the specifics, but it can be done very quickly. And what it does is it's trained how to identify how a number is written. So not how, but what number is written. So if you write 3, it will compute and label what you have done as a 3. And so, like I said, it can be done very quickly with conventional AI like Python, TensorFlow, or other Python libraries. But if you use Brian, unfortunately, since the particularity of the simulation of a brain cells, what happens is it's very hard to parallelize. Okay, so running in parallel is, for all intent and purposes, impossible. What you have to do is advance like a step and look what is going on at that step time. It could be like a millisecond, it could be like a femtosecond. Obviously, the more you simulate smaller times, the more you'll be precise. But the counter, but not the skills, but the problem it will generate is that it will take forever to simulate. So you have to decide what kind of simulation time you want, and at every steps you compute the now current state, and then at that moment you can realize, oh, at that point there is no excitation into the 10. There is 10 neuron at the end that one of them will be excited, and it will then represent what number it is identifying. So it's a 3, it might be the third one. Okay, so the problem is like on my computer, it wasn't a fast computer. It was at the time like a Intel 9th gen 9975. It was a mobile one, and there were a 2060. I think it was like 6 gig of RAM, but it took like something like 16 to 18 hours to train the MNIST that the same computer could do in less than 2 hours with like TensorFlow or stuff like that. So if you're interested in the concept and trying it out, this is very interesting. Brian is very powerful, and there's a lot of example too you can watch. All right, so I did that, and next fall I will complete my master with a class on IC design. So IC is integrated circuits. So like a CPU is an integrated circuit, a GPU is an integrated circuit, but there is a lot more integrated circuits that exist. For instance, I will show you what in the same time what an FPGA is. So let me go over here, move that wire for you. So here is an FPGA. It's the FPGA I will use during in this channel for a while. It's the board is made by Digiland. It's a Arty Z7. Z7 is in relation to the FPGA that is made by AMD. Prior it was Xilinx. You will see a lot of Xilinx AMD cross-pollinating. It's normal. So this chip here is an IC, and this is the FPGA. So I will move it out. So it's a ZinQ. The how can I say, the main feature of the ZinQ is that along with the FPGA fabric, so we will come to that later, but the FPGA the ZinQ has contains in the FPGA fabric, but also contains two ARM Cortex A9, sorry. So it has two CPUs inside, so it can run, for instance, it can run sorry, Linux, for instance. Okay, I think Xilinx or AMD as tools to install PETA Linux. I have never tried it yet. The only thing I use, so this is the card that I will use, but one of the cards I'm more familiar is the Zibo. So it's a little bit bigger. In this one, the FPGA seems to be the same size, but it's actually smaller. But the cores are slightly faster than the other one. You can look that there's a lot more IOs. There is those here with this one. There is a USB type A here. There are two HDMI. The other one has also two HDMI. Three Jack 35, I think. There's another PMOD here. Some switches, some button. So this and this is a connector for video, I think. There's a micro SD card too on the back. But this one, but the reason why I don't use this one is because it's a little more expensive than this, and also this is not mine. This is one that we use at our university, and with this one I made a kind of like an NES. So the first Nintendo console that was in the 80s. We did something similar in our class. So and for since the past 3 years, I gave the class. I am the like the teacher, not the teacher. The term I don't remember in English, but I do. It's called like a tutor, I think. The term in English. All right. So. So this is the FPGA, but this is the DDR3, I think, something like 512 or 256 gig of RAM right there. So this or this one. So I really talk about the black ones, okay, not the gray ones. The gray ones I think are capacitor, but these are one of those is the quad SPI flash. So we will see later that this chip, when we turn it off, it loses every configuration it has. So an FPGA, what you can get of this is that the circuitry is a lot like RAM. In fact, it's basically memory with some tweaks. And so if I want to disconnect and reconnect my FPGA and make it work, what I have to do is use a separate chip that will contain the program of the FPGA, and when it starts, the first thing it does is, hey, are you programmed? No, perfect, take this. So one of these two as probably as the flash. I think it's something around 32 mega. I don't know. We will check the data sheet later. All right, one of those. So this one could probably be, for instance, the controller of the RG45 connector here. And in the back, we have other ICs. So all of these are ICs, okay? And not to be confused with those that are capacitor. No, not capacitor. These are probably just resistance. And we have on the other side, I think those are, they might either be what is called a regulator or capacitor. And there's other much smaller resistance over there. All right. So the class I will take will help me design those chips and at the end I will be able to make from the design of the of a chip up to its production, and once the production has been done, I can create the PCB. So the PCB is like the board you see. That is a PCB that use that chip. So it's for me it's very interesting stuff. All right. So what is the FPGA? What is the FPGA goal? So if I was, let's imagine for a second I want to make a simple CPU. Okay, I'm in the 80s. I think I will show you the image. If I found it, it's a very, very interesting image. So I think it was the 6502 MOS. Let me look. It was a very interesting time when they did the first CPUs and stuff. I cannot find it here. Was it the 6502 or the 404? I don't remember. Maybe it was the 404. Wait a second. So let's say we go to okay. Can I find block images? It won't be long. It is. There's nothing. I can find it. Okay, so if I find it, I will send it to you. But the interesting part that was back in the days is when you have to create a CPU, what you have to do is define at the transistor level what are the circuits. Okay, so just a second. All right. So, for instance, there is a circuit that will give us the possibility to add numbers. There is a circuit that gives us the possibility to shift bits around. There is circuits that will handle the access or not of on a wire, or what we call a bus. Or a bus is a set of wires that can pass data in parallel. And there's a lot of different kind of circuitry we can do, and those can be then put together to do something again yet as more features. So for instance, in the CPU you will have the ALU, the controller, and the memory access. Okay, and so just think about it, like just one transistor, you can do much with it. Okay, so for instance, if you want to make a what you call an AND gate, that is very basic, you will need something like not an AND gate, sorry, an NAND gate. An AND gate is a gate that returns it returns I don't want it returns I will make a little schema, sorry about that. I'm not connected yet. It won't be long. Oh, did I turn it off? No. It's right here. All right. It won't be long. It should be working. Let's go here. Okay, then go back. Perfect. Okay. So so to be able to make a circuit, you will need what is called gates. So there are, let's say, three basic gates, but and OR and NOT. There are others, and in fact, we will probably tackle this concept later, but there's also the NAND gate that is a universal gate. You can do every single gate over here. Sorry, all of those gates here can be done by this gate. All right. So the AND gate, what it does, it takes two inputs. So let's say I have A and B, and I want to do A and B. All right. So symbols that is used is often this one, or in like a what we are used to in mathematics, it's the dot, like a product. All right. So for now, what you have to know is, and again, it's not totally true, but in a circuit, digital circuit, a signal is either 0 or 1, and usually 0 means like no current or no charge, and 1 is there's a charge or there's a current. All right. So these are the values A and B can take. It's all the possibilities. Okay, there is 4 possibilities, and the AND will. Oh, sorry. I did a OR. Why is it working? All right. The AND is true only if A and B are true. The OR is a little similar. It's false only if A and B is false. All right. And the NOT. So if I say NOT A, it reverses the signal of the AND. Okay, the A. Sorry. So now if I want to do a NAND, it's a NOT AND. So I want to do A, NOT, and B. But in fact, I think the right way to see it is NOT A and B. All right. So we will flip those bits here. So 1, 1, 1, 0. All right. So the NAND gate is what is called a universal gate and can be used to create all other gates. But for now, to simplicity, we may use, for when we will present some examples, on the AND or in the NOT, and further down streams, we will probably look at how the NAND is what is called a universal gate. All right. Perfect. So if I want to make a gate, I will need transistors. So a transistor, there is, let's say, whoa, sorry about that. I think the pencil is broken. Why does it work? Okay, perfect. So the transistor will have a tension here, and may or may not have tension here. Okay, and this and for now, again, sorry about that, there is 2 types of transistor. I will present a simple version so you can understand and grasp the concept, but you have to know that there is a little bit more complication around transistors. Okay, but this is the main idea. If I want this signal be A and have another signal here be B, and I want that here to be 1 if A and B are 1. So I want to make an AND gate. It's easy. I will connect this here, and this will have, let's say, 3.3 volt. So if A is 0, current won't pass through here, so this is 0. All right. Even though this is 0 or 1, doesn't matter because it has no voltage on that segment here. So if A is 1, then if this one is 0, the current won't pass, but if it's 1, the current pass, and then we have a 1. All right. If I want to make an OR, what I will do is put them in parallel. So I have my A here, I have a B here, all right, and these go here. So there might have resistors. This is not the goal here. The goal is that if A is 1, here there's a 3.3 volt, 3.3 volt here. The current will pass here. If this one, the current will pass here. Either way, either is A or B, 0 or 1. At least if one of those are a 1, it will output a 1. All right. So this is a concept here. Those people in the 70s and prior to that, when they had to create a CPU, they literally had to use pieces of plastics. Like this is, I don't know the size of this, but let's say it was probably like around 1 meter, so 3 feet by 1 meter. Okay, sorry, it's not at the scale. Okay, so they design it in books. Let's say they designed the AND gate, they designed the 8-bit additioner, they designed the controller, they designed everything, and then someone took an X-Acto, so like those lamb retractable, okay, and cut tiny holes, and all of those tiny holes represented transistors, like part of transistors. They did all of this all around that piece of paper, or not paper but plastic, and put it in the oven, so it will be shrinked to a size where all of those holes would be, I don't know, 1 micrometer. All right. At that point, when it was that close, it was the mask for the CPU, and there were processes where lights were passing through, and there were a disk. Whoa, sorry. There were a disk of silicium. That disk had some coating on it, and that coating will react. It was a coating. The term is photoresist or photo not resist. In fact, it will be destroyed when in presence of light. So that will be shrinked, and then will be put on top of those silicium disk wafers, we call it, and light would be would pass through the mask, and then a process of cleaning up the disk and then redo the process would yield some amount of CPU. Okay, and today it's the same concept, but instead of making it with X-Actos, there are machines that are very, very, very precise, and one day we could look at it more in details. If you want, you can go back to the Anastasia and Tech YouTube channel. I think there is one of her video that explain it. There's another guy. I think it's. Wait a second. Okay. Yes, this guy. So let me show you here. Screencast. Okay. So Agenometry, it's another YouTuber which present technology in that were developed in mainly in Asia, but they explain how TSMC with the company ASML, not ASMR. ASML is a company that comes from Germany, I believe. There is a lot of politics around that company, but it's the only company that can do the the type of transistor we have in CPUs today. It's the only company that sells to both TSMC, Intel, and Global Foundry and stuff like that. And I believe that Agenometry and Anastasia in Tech explained very well all the information we have about those technology, because you have to know it's very, very secretive. Okay, perfect. So to conclude, like my introduction, what my master degree is, I will have to write like an essay or a memory. I don't remember the term when it's a master for a course master, but it's how what are the not the irritant, sorry, this is French. What are the element that add friction for enterprise to adopt FPGAs? Okay, so for instance, the company that I work with during 6 months did working on a robot, and that robot was used to help operator drill through like from inside sorry from inside a pipe. Okay, so it's a pipe that will get fresh water in it. So there were a technique where they would put like they will clean the pipe, put a like a coating around from the inside of the pipe, and then that robot will walk down that pipes and drill from where the like the little pipes goes through to the like houses on the street. Oh, okay. So that robot used Latte Panda. Okay, so Latte Panda is like a bigger Raspberry Pi. It's now it has a new the Sigma one seems very, very promising. We use the Delta. So those are like x86 SOM, I think. No, see, small board SBM. Okay, and so it can be very, very fast. I think like the one I had before, the Delta, okay, was like 3 times faster than the Raspberry Pi 4, and run Windows at like 8 gig of memory, I think, and that was their first choice. All right, and but it's not very CPUs are not very efficient to handle video streams. So the first robot they had 1 camera, the second version had 2 cameras, and the problem is not the problem, but if we want to make it work better, if we want to be more efficient, an FPGA could have a lot of gains. So for instance, will consume way less energy than a CPU to handle, for example, 2 or 3 HD feed. Okay. And the problem was that the day I arrived, finally they decided to keep the same Latte Panda 3 because in the specification it answered the minimal requirement they had for their project. So instead of working on this, I work on other things, and like I said, it didn't give me any information about. It gives me 2 things. First, enterprise that doesn't have people that knows how to use FPGAs or just knows what are FPGAs are not very interested in working with them. That is the first point. And second, this is something I learned with time in the past 2 years, is that developing FPGAs is very hard, but also very, very expensive. So the card I showed you earlier, like the Arty, the whiteboard, this one is in Canadian dollar, $500. Okay, the Zibo I showed you, that has a smaller fabric but a faster CPU, like slightly. I think it's like 667 megahertz against 650. Like it's like negligible for what it's worth. But it's there. So the Zibo is 700 Canadian dollar. Okay, so just the entry point is very expensive. A Latte Panda was, I think, around $200 to $300 back 2 years ago, and it was during the pandemic, and it was not during. It was during the recovery of the IC crisis we had in the early 2020s. So it was a time, for example, that it was like impossible to get a Raspberry Pi or a Raspberry Pi compute module. It was very difficult at that time. So those boards were very interesting because they were not that they were expensive, and the fact that a Raspberry Pi can be under $100, but I mean you can get it. That's the plus, and it's 3 times faster. So you can run Linux if you want to on that machine. All right. So and like I said, it's very expensive. So I use AMD technology. So XenQ. There's Intel that I've bought Altera that has its own infrastructure, and there's a little one. I think it's Lattice. There's probably other one around, but this is the 3 main I know, and all of these companies give software to help us develop on FPGA free of charge. But there's a big asterisk. First, if I'm developing on this $400 board, no problem, everything will be supported. If I buy like the high-end Versal ultra scale FPGA that has so many gates, you can simulate you could simulate, I don't know, a x80 fully fledged x86 CPU, for instance. Okay, that costs like in the thousands or tens of thousands of dollars. Then you will have to pay for specific IPs, so blocks of like you can imagine that in the FPGA there are tools that can accelerate the development of project for instance, in my little FPGA here, there are what is called a DSP. It's digital signal processing, I think, and those are actually multiply and accumulate tools. And there is like 120, about 120 instant of that specific block, and this is free of charge. But if you go to the high end, there are tools that are very more powerful, and then you have to pay license for this. So you will have Vivado. So the software we will use is Vivado for now, and Vitsys, that is the so Vivado is for like the hardware part where we simulate circuitry, and Vitsys is the part where we code in C, or I think we can also do assembly. All right. So, but those tools are free, so they are not that. They are useful, but they are not so powerful. Okay, there are other tools that give, for instance, way more information about delay propagation, and that can optimize way more stuff and find problems very early in the process of developing an IC. Okay, and for instance, there is a software that is called Synthesis. No, not Syncity. That is a movie. Simplicity, I think. Simplify. Why? It's from Synopsys, and a simple like entry level license. It's $9,000 US dollars. But if you want the Simplify Pro, it's $19, and if I'm not mistaken, it's it's annually. Okay, so if you are three software engineer that works, not software engineer, sorry, a computer designer or whatever, and you work in a company, right there it's 19,000 times 3, but this is like nothing in the budget of it's not nothing obviously, but the cost of engineering, the cost of research, there's a lot of people around this. There are other software you need to use. The FPGAs, making PCB, just the fact of making PCBs is very, very expensive too. So and all of that process is usually to make an IC. So the main goal of the FPGA, often so, is to test, hey, we want to do this kind of tool, for example, and we design it and test it on the FPGA. That will cost us very few dollars, but less dollars than if I would use the same design, send it to a fab, like TSMC, that produce the wafers. Each wafers are in the millions of dollars, and then you will test them and see that you made errors. It's very, very, very hard to make like a CPU, a GPU, or an IC first try. You need to make some adjustments, and so every time you make that process, it's millions of dollars, a lot of delays. If you have an FPGA, you don't have that problem. You buy the FPGA $5,000, you pay the license $19,000, you pay the engineer to make his design, test it, and at a point where all the problem has been identified. And Simplify, I don't remember the name, sorry. I think I closed it. Simplify from Synopsys. It's the kind of tool that will identify a lot of problems that Vivado and Vidsys won't. Okay, so that's one of the problems too in companies, is that they don't have the knowledge to use those technologies, and they are not willing to invest thousands. Like it's all. I would imagine that if a company wants to enter that market, like want to try FPGAs to solve problems, it will be usually $50,000 up and in investment, and that is very low, very, very low. Okay, so now how can we help democratize that technology? That is a bit what I would like to do in the future. All right. So the main focus of the stream today is, again, a quick introduction on what is an FPGA. We will not be very far on the concept, but we will make this little one work, and something very simple. We won't be coding the FPGA per se. Like, the only thing I want to do for now today is connect the USB, be able to talk to the CPU, the ARM, be able to see the fabric, and then with a little program that will be bare metal meaning it will run without any OS on the ARM directly. So a little program that will just send messages on the terminal. So UART like I don't remember UART is RS-232, I think. Similarly, it will pass through the USB. All right. If we have time, we might also try the so the terminal. We will be able to send data, and then it will be the ARM CPU will answer back like you said, and repeat what we said. Okay. So if we have time, either way, we will see. Okay. So first of all, what is an FPGA? And now I want you to pay attention of the fact that the Zinc queue, so the the chip we have on the Arty Z7, the board. That chip has 2 ARM cores and has a FPGA fabric from Xilinx. And like we will demystify everything in there. Just a second, there it is. So this is the board, okay, on the Digilant side. Digilant is the company that makes that board. It uses the ZenQ710 SoC system on chip. So the mine is the Z7-20. So it has more feature in it. And what you can see is that there are some terms that are thrown at our face right now: logic cells, DSP slice, and block RAM. So you can see that the Z720 is about twice, in fact, have more than twice the capacity of the Z710. And if you remember earlier, I showed you the ZIBO that we use at our school. It has a Z710, so it has less logic in that. Okay, so we can see here that there is the CPU are clocked at 650 megahertz. There are 512 megabyte of DDR3 using a 16-bit bus. So what it means is that so DDR is double the data rate. So in the first, like when there are a rising edge of the clock, the first 16-bit are sent to the CPU, and when the clock is falling down, so the signal goes from 0 to 1 is a rising, and the falling edge is when it is to 1 down to 0. So that will send 16 other bits. Okay, so since the Cortex A30 Cortex A9 is a ARM CPU that has a 32-bit bus address. Okay, so the DDR uses a 16-bit bus to connect to the ZenQ processor. We have a 16 megabyte, so it's not 32 megabyte, it's 16 megabyte of quad SPI flash. What you have to know is that the flash is used to program the fabric in the FPGA. Power, there's a lot of ways. You can either power it through the micro USB or through the 7 or 15 volt power supply that you could have. And there are some button switches, LEDs. There are also 2 RGB LEDs. Those are fun. You can change the color. And what is interesting in the Arty Z7 is, instead of having like the video output, there is like a Arduino shield connector, so it can connect a lot of stuff that people use in Arduino. So so one second, I will show you something quickly here. So one of the things Digilant have made is those connector here. Those are called P mode, and on the website of here on Digilant, you can go in I think you can see them. PMOD expansion module here. So Xilinx propose a lot of modules that can connect to those connections. For instance, I have 2 here. Let me show them to you. Okay. So one of the modules I wanted to try was this one. This is a Bluetooth module, so I can plug it in here. And when we will use it in the future, I will program the FPGA to say, hey, those pins are connected to this module. So I will say pin like P mode 2 or 3, configure it as SPI or something like that. And at that point, it will be able for me to connect and communicate with this module and connect like on a cell phone. Okay. One other module I wanted to try was this little one. This little one is like a little OLED display. I think it's like it can make a 1/9 of some 10 characters. Again, I can connect this one here, and I will be able to configure that P mode and use it. So you see that I have 2 P mode here, but I also have those thing here. So the Zibo doesn't have it. The Zibo, it has this connection, it has those connection here, and a lot more P modes. So 1, 2, 3, 4, 5. So this is interesting for in the Digilant architecture. But this one, I can go on Sparkplug or some Arduino shops that do Arduino shields, and then put it in this these 2 connectors here. Okay, perfect. So if I come back here, we come back to our card. So Digilant do the board, but the FPGA is made by AMD, or you can say Xilinx. Okay, so if I go to let's say DigiKey here, so I can get the datasheet, and this is a datasheet for a series of ZenQ. So the S notation here are about there is only one CPU core instead of 2. When there is no when there is no S suffix, right? It means that there is no sorry, I was distracted. So when there is an S, there is only 1 core. When there is no S, there is 2 cores. All right. So one of the things that I am interested is to look at the ZenQ 7-20 SoC overview, this document. I hope it will work. Perfect. So this one, it's really weird. I don't know why Digilant does this, but that datasheet is just the datasheet that is needed when you do a board. So the AC and DC switches. But when you want to select what capacity, it's better to like either look this document or there's other more thorough documents. So this is the ZenQ family. So you can see that our is the Z7-20. So this is this one, the part number. So the fabric, if you will. Dual core ARM Cortex MP core with core site. I have the slowest one. So what is weird is that it says minus. I think that mine would probably be underclocked, because here it says 667, but mine is 650. So maybe it's a yield that doesn't pass the test, and they can sell it cheaper. So here are the information on the CPU core, etc., etc. So now you will see Artix and you will see Kintex. So there are others family of FPGA. Sorry. And Artix, it's like not the lowest tier. I think Spartan is the lowest one. Artix is just a little more feature rich than the Spartan, but indeed less featured than the Kintex. And there is I think there is another one, but not in the ZenQ series. So now we will look at what are cells, what are lookup table, flip-flops, block of RAM, DSP, what all of this means. Sorry again. I will take a little glass of water. Sorry about that. Just and I'm back. Okay, sorry about that. First, we'll just talk about the PCI Express here. You will see that our board doesn't have one. It's just a way to communicate with a PCI Express, the same connector there is in your computer. And for what I understand, you could use this to indeed add your FPGA into your computer and do stuff. We will talk about this. We'll go deeper in this sooner. There are ADCs, so very so often when we have an FPGA, we could have data that comes in that is analog. So the ADC will convert the signal coming from the analog port to a digital signal. And you can see that all of the chips have ADCs, and those are 12 bits. Okay, so that's the range they can operate. Okay, so what are programmable logic cells? What are lookup table? What are flip-flops? And what are block RAM, DSP? What is everything? We want to know. And we will start with LUTs, so LUTs. So let me go back to here. We will reconnect. Sorry about that. Here, start. 3, 2, 1. All right. Perfect. We go back here. Okay. So what is a LUT? It's a lookup table. Okay. So the FPGA will have, we will define an inputs, outputs, and interconnection between everything. Okay. So for instance, our FPGA, I believe, have 6-bit LUTs. Okay, 6-bit LUTs. Okay, and when you have 6-bit, what it means is that we can have A, B, C, D, E, and F signals. All right. Earlier we saw the AND gates. Okay, so the AND, I could make a symbol for that. This is the symbol for AND. So there is A, B, 2 signals, and there is a output, let's say O, and this output will be A and B. Okay. But here we have 6 entries. So how many combination I can do with 6 entries? It's 2 to the power of 6. Okay. So how can we compute it quickly? It's easy. We just start with 1, then times 2, 2, times 2, 4, 8, 16, 32, and it looks like it's 32. So there is 32 combination. Okay. Perfect. Is it right? I think I missed a number. Let me double check. I don't want to say stupid stuff. Oh no, I said stupid stuff already. So it's 64. Okay. I think it's the stress of the stream. So 64 combination. All right. So if I want to make an AND gate with that LUT, I will lose. Whoops. Sorry, I will lose all of this. Let's say we use that color, like so, and I will be the output here. Okay, so we can imagine the LUT like just memory. Okay, it's just very, very fast memory, and so there is like we could imagine that there is the address 0, 1, 2, 3, 4 up to 63. Okay, you see that I start at 0. It's simple. If every variable are 0, okay, so A through F, okay, are zeros, but the value is zero, sorry. If I have 1, 2, 3, 4, it's 1. Then it's 2, etc. Okay? It's 3. Okay? So what will happen is that A and B, if they are 0, so let's just we will do the full example. Okay, so we have 1, 2, 3. We just remove this here, and we will do some. We will do like 16. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 for starting. Okay, we will see if we do more. So let's say that this is A, this is B, C, D, and E, and F. All right. So if we have we want to make an AND gate. Okay, AND A and B, and we don't care about all of C, D, E, and F. Okay, so we will just look at those two here. So this will output in O value 0. Okay, in fact, let's write it like that. If A is 1 but B is 0, we have yet again 0. Here we have 0, and now we have 1 here. So that is the AND gate, but unfortunately the FPGA has 6-bit LUT. Okay, so the LUTs are 6-bit. There are some that are 4 bits, but this one is 6. So if I use those 2 and 3 just to make an AND, I will lose all the possibility that those bits will give me. Okay, so one of the tasks of the synthesizer, so Vivado, is to try to maximize all the LUTs it can use. Okay, so here we have 0, 0. So when C is 1, it doesn't matter. Okay, we have to make it 0, 0, 0, and 1 again. Why? Because those two are 1s. Okay, so LUTs are little tables of memory that are very fast and can be interconnected. So I can have that LUT here connect to another one. So if I move this here like such, could have here another 6, 1, 2, 3, 4, 5, 6 that receive this output, but could have other outputs that goes into there, or could be inputs from the FPGA, and one here, etc. And that one will output somewhere else. Okay, so one of the things I want you to know is that the FPGA will have inputs. Okay, usually it's on pins. Okay, so if you look at an FPGA, at the bottom there is a lot of little balls like such. Some of them are for power, some of them are ground, and a lot of them are for IOs. So either it is an input or either it is output. And the power of an FPGA is that we usually can reconfigure all of these pins that are IOs as an input or an output. Okay, so this is very interesting because it gives us the versatility to design and use what we need in certain part of the FPGA, but in another project it could be somewhere else. Okay, so the FPGA have input. Then in the FPGA, like I said, the FPGA has a fabric, and that fabric has, for instance, LUTs. Okay, so with input from those pins to the LUTs, I can then take the output of LUTs to other LUTs, and at some point I will probably have like the last LUT here that will connect to an output, a pin that will give the signal out. Okay, So LUTs are very simple. Those are organized in what is called a CLB. Okay. So for now, I have a brain fart. I will tell you exactly what CLB stands for. Okay, configurable logic block. Configurable logic block. So what I suppose is that they are very different from company, but the concept is very similar. Okay, so we will have some LUTs, and at some point we will have what is called a one or more demultiplexer. Okay, multiplexer or demultiplexer. So what are multiplexer and demultiplexer? I will just show you the is this one a good example? Just a second, I will make sure. No, that is not good. What about this one? Okay, yeah, I think this one could be good. So just a second, I will add this here and show you. One moment. Okay. Here, like this. Okay. So those symbols are not right, but the idea is the same. So let's say we have a lot of data coming from different sources, and I want to select one of those lines to continue through. Okay, so there is 6 lines here. There is a multiplexer that will receive a signal. So in this case, they put it in the bottom. So they need n signals to select which one of those lines will go through the output here. So this is a multiplexer. Okay, and this is the symbol I showed you earlier. So this one here, this is a multiplexer. Okay. Usually what we do, say those input will go like that, and there is another signal here that will switch whether this one or this one. So if it's 0, we will take that route, but if it's 1, so it will take this one. Okay, so that is a multiplexer. A demultiplexer is the other way around. So we have a data that is coming, and this is the symbol. We'll have a signal here, and this will pass here or here, either way. All right, perfect. It's very quick, I know. I could probably send you some video that explain this in way more detail, but if you understand the gist, it's okay. Okay, perfect. So now, just a second. So you will need so the CLB has a series of inputs. So here, like this, and very so often those are like that. Okay, and after that there might have some sorry about it here. There can be some module that are custom to the company that so Xilinx and Altera or Lattice might have some more or less complex or feature-rich block here. So considering what we need to do, the CLB will have a different set of those multiplexers like this. Okay, and there might have other LUTs, but at some point there will be or will not have what is called a flip-flop here. A flip-flop, what is it? Is a it's a circuit that keeps a value between two clocks. Okay, so if I have a clock signal in a circuit that is not sequential, that is like an AND gate, at the moment one of the input change, the output will change virtually instantly. Okay, a flip-flop will keep it up to the next signal clock, and sometimes might not change if there is not a write enable. Okay, so let's unpack this. So we have here a flip-flop, and this is the output, usually denoted Q, and we could have two signals here, a clock signal, and here we could have what is called a write enable. So this is the input here. So very so often it could be called D for D flip-flop, but there's other type of flip-flop, so I will just make put it to I. So this input will try to change the value of this flip-flop. Okay, so this flip-flop has a value Q at this moment. E change, so E, sorry, not E, I. So I changes, the clock is set to 1. If the write enable, so the write enable needs to be set, so we will authorize the change of the value Q. Okay, this is this is a circuit that is at the root of all memories. Okay, so your RAM memory, not so much your flash and NVMe drives, but your registers in your CPU, your L1 cache, L2 cache, L3 cache. Most of what you use as memory are using flip-flops such as these. Okay, so you can be either you can either have a path that is defined by the synthesizer that says, okay, we take A, B, pass it here. We don't have to use the special here, so we go here, and then this one here, and we could at this point, in fact, either go to the flip-flop or directly through an output, for instance. Okay, so here would be would have something like that will go to output. All right, so it's called an unbuffered output, and this is a buffered output. So a CLB, what it does is give the possibility to be each of these components can be programmed, and that is what it will be saved on your flash memory. Okay, you remember, if I go back here, sorry, like this, if we go back here, no, sorry, here, we go up, we have 16 megabytes of flash memory on the board, and that flash memory is used to reprogram the FPGA once it boots. Like I said, it doesn't keep the program in the FPGA. FPGA is basically memory. Okay, so if you want to say, for instance, okay, the circuits I want to design, it's an AND gate, and I want it to be buffered. It will take those two input, go through here, go up here, go down here, and go through and maybe be used in another LUT somewhere else. If I would say, no, I want the AND gate to be at output to the pin number A16, then it will go back here, no, sorry, not here. It will go up here. This, don't forget that this module is a special module that the FPGA gives. Some might have advanced features, some might be very simple. Okay, great. So if we go back here, we now have explained very high level what is a programmable logic cells, a lookup tables, and a flip-flop. So a block of RAM, I won't, and the DSP side, I won't talk about them very in details. What you have to know is the block RAM is a 36 kilobyte of data available, and sometimes it is better to use a block of RAM instead of many LUTs. Okay. DSP slices, like I said, those are multiply and accumulate operations. So we see that the DSP slices given by Xilinx are 18 bits by 25 bits. And our FPGA has 220 of those DSP slices. So it's able to compute, multiply, and accumulate very efficiently and quickly, and they are 220, so I can do that. I could, like, in theory, simulate a neural network with 220 neurons and use all of those to do it. There is other limitation, but this is the gist. All right. And those are statistics in the performance. I don't know what the GMAC is, but for what we will do, it's not very important. It's just for is it working, not for performance yet. Okay. So that is a little bit about what an FPGA is, and the concept is that we need synthesizer to define how our program will work on the FPGA. So define which CLBs, which pin goes where, etc. Okay. So we pass all of this. What I wanted to tell you is you maybe have used FPGA without knowing it. For instance, there is this company that makes a very interesting gadget. Is a I think the company is Pocket or Analog, I don't remember, but this is a Game Boy-like console and held, and inside there is a FPGA that comes from Intel. I think it's a Cyclone 5 or 10. I don't remember 100%. But what is very cool is that the FPGA can replicate exactly how the actual Game Boy chip was doing. So what is very interesting is that it's not emulated. You can take one of your past cartridges, put it in there. You need extensions. So some of those are inserted inside the consoles, and those can receive cards from, let's say, Game Boy Color, or other supported handheld, and it will play it like virtually exactly as it was intended. Okay, so it's not emulation. It's the FPGA is reprogrammed to exactly run at the signal level the game. So it's very cool. So if you have that kind of tools at home, that is very interesting. Other things that you might have encountered, it's a little more niche, is if you are aware of back in the days when cryptocurrency and Bitcoin and stuff like that was very the hype, there were a lot of ways to mine in those technologies. Most of the people use GPUs because usually what it has to be done is some computation that are very parallel can be parallelized. Sorry if I pronounce it correctly. But one of the problem is that GPU are not optimized for crypto. They are optimized usually for gaming. Okay, so now they have a lot of AI capabilities, and this is due to the fact that how a game works, how an image is created, and I mean not generated by AI. I mean like actually making a frame from a video game like Minecraft, for instance, has very similar computation than AI. Okay, so the only thing that was needed to change in GPUs is the ability to, for instance, instead of using 32 bits or 64 bits data value, in AI we want to reduce it at a minimum, so 8 bit, 6 bit. There is instance of AI that use only like 1 or 2 bits as a value. I don't know how you can do something with 1 bit, but it seems to be something possible. And so back in the days, and I think I found something, I don't know how much it is the same back in the days, but there are cards or materials that are specialized, for instance, to mine a Bitcoin. Okay, so Bitcoin uses SHA-256 as its base algorithm. So those are specifically made to take as much power possible per instruction. Quand on s'en va vers... sorry, I suddenly start to speak French. When every single instruction that is made in those cards or those ICs are to make SHA-256 as quick as possible, taking less energy as possible. So every how I can say it, every link or signal or operation that are useless in a GPU, you won't find it there. The drawback is that if, for instance, you have to change your algorithm, like Ethereum did like 2 years ago, I think, as I remember. But if you bought one of those cards that was specifically tailored to Ethereum, that card is a brick that can be used as a brick. It's very sad. So if you use GPUs, you will use a lot of energy because there's a lot of things that are not optimized. All right, so we can do SHA-256 in a GPU, but it might take, for instance, 39 instruction, 39 clock cycles, and use, like, I don't know, 20% more memory or data path signals that the other cards didn't use. So it's very less efficient. Now, the FPGA is very interesting here because we can program it for SHA-266 exactly like the other card. But if tomorrow Ethereum change again, I just need to change the circuitry of my FPGA and optimize it for that new algorithms, and now I am as almost efficient as those here. Okay, you have to know it's obvious that a ASIC will be better. So you do a chip that has been made 100% like transistor level, it will be more efficient than FPGA. Sometimes you don't do enough of those machines to justify the cost of making an IC. Right? So, and one more thing, I didn't find the reference. I'm pretty sure I saw this somewhere. I couldn't find it though. I don't remember if it was on a x86 system or maybe Altera that makes ARM server CPUs. But how can I say that? The motherboard had an FPGA on it. The FPGA wasn't used for the customer, not for the motherboard. The motherboard wasn't making available that FPGA, so the user would use it. It was used to give the possibility to the card to change functionality on the fly through that fabric. Okay. So if I find it, I will show you the that motherboard, but I couldn't find it earlier. Okay. So now we will be talking about Vivado. So it's time to go here. The main goal we want to do now is take that card here, plug it on my computer through USB, program it in a way that it can send me a message like hello world on a terminal. Okay, that is the main goal for today. If we have time, we could do one more step, is from the terminal send something to the card and then resend it back so we can acknowledge that's been received. Okay, so what we need to do is go to the Vivado here, and you can install it on Windows and also on Linux. For now, I'm using Windows because my Linux system is not up to date and very flaky for the foreseeable future. What I will probably do is in some, let's say before Christmas, what I would like to do is stream all the process of making the Vivado and Vitis Suite work on Pop OS. But for now, I just don't have the time. It's time consuming a lot. So for now, we will have to endure Windows for those who like it. It's very fun, but it's not my favorite. Okay, so we will create a project. And all of this, what I do today, was very inspired by another YouTuber that I found. Like it was, I think, late December about of this year, and it really helped me go a little bit further in FPGA development, and it opened my eyes on how much I don't know, how much thing I don't know. It's so big, it's crazy. So let me find this for you before I go. It's my subscription. Sorry. Okay, here. It won't be too long. Sorry about the delay. Okay, no. All right. Okay. So this is the channel Field-Lab. This guy is very great. He does PCB design. I think he did his own like dev board like this one. Sorry, this one, but not this one obviously. But he did his own like ZinQ board. And in one of this video, he what he does is do what is called a bring up. So it tries to like activate every single functionality. And at the start, at that video, the only thing he does is what we'll do today is make sure the UART works. It can be programmed through USB, and the card can send data. So one of those, though I don't remember which one. You couldn't look it up, but very interesting channel for PCB design, and a lot of things that I didn't know during my class of PCB design. I would love to have found that guy. It answers everything very, very, very clearly. So if you're interested, you can check this out. All right. So now I will create the project. I will call it a Arty fun. Let's say that. I usually use the here. I usually put my project in C, in the drive C. You could use D or whatever other, but not in your home directory in Windows. It's usually not a good idea, especially if you have Office like OneDrive. It will be a tug of war between Vivado, Vidsys, and OneDrive to make your file works properly, because there's a lot of stuff that's going on, and it's very often breaks. In fact, I'm pretty sure if I go get a OneDrive, it will make me a warning. So I put it there. In Linux, you can just use /home/ whatever you want. Usually there is no problem with that. So working is my working directory. HW is hardware. So all my the Vivado project will go in hardware. All my Vidsys project will go in software. So it's SW. In software I put all firmware /software project. Okay. Now we can next. Just a second. All right. Okay. So now we will use a RTL project. We won't have any file for now, and I don't click this. Maybe I should, but for now I won't do it because I've never tried it. There is like a problem with Vivado 2023.2 and Vidsys. I figured a way to walk around it, but I won't try other things for now. Maybe later in another feed we could tackle that problem. So I click next. Now I'll need to get my boards. So I already uploaded all the boards from Judident as far as I can go. So it's already here, the Arty Z7-20. Like I said, there's a lot of tutorial on the internet to how to do that. But when I will set up my Linux instance, I will show it you how to do it. So go to next. So it's a little report that says that we have all this, we are happy, cool. Just click finish and the project will be created. All right. So a lot of things that we will do today are things that there's not really like a intuitive way to do it. Like you cannot pop this without ever reading anything and start with this. You need to know how it works. Okay, so for now, the things I will do, I will try to explain as much as I can, but what you have to understand is I won't be doing or going into very deep explanation. That will be first something that I probably need to do by my own. What I mean is that there's a lot of things I don't know, first. And second, the level that we want to do for now, we don't need to know everything. Okay, we can do a lot of things with little knowledge. Okay, so the first thing we need to do is a block design. So in this section, we click on Create Block Design. We can give it a name. I will say Arty Z7 Block Design BD. So okay, it will take some time. And now we have a new interface that gives us the possibility to create what is called a block design. So a block design, if I make a little place like this, gives me the possibility to add IPs, so intellectual properties. Like I said, Vivado brings a lot of free IPs, and the card that we use, we can extract everything that this little FPGA has inside with free IPs. So that is good news. So the first thing we want to do is add, since we want to communicate with the ARM core, ARM CPU, we will need to add and activate that functionality of the system on chip. So if I could just make another drawing. Every time it disconnects, it's sad. I'll try to find another way later. Okay, start broadcast. Okay, so go down. Okay. So what I wanted to explain here is that whoops. So we have the ZinQ here. The ZinQ has a lot of stuff, but the things that are interesting is CPU here, and there is the FPGA fabric here. Okay, and everything needs to be activated by the fabric. So even the CPUs needs to be like we can imagine or think like the FPGA need to instantiate those instances of CPU core that are available on the chip. Okay, so it requires two things. One, the ZinQ processing subsystem. Okay, subsystem. It is away from all the SoC. So all of this is the SoC here. Tell the SoC that those are activated. Okay, and to do this, we need to pass through the FPGA. Okay, and another thing we need is the processing. I think processing reset. Blah blah blah. So in order to orchestrate everything, the CPU has a way to be started and restarted. We need that IP to handle this. Okay, perfect. So let's do this. We go here and we just need to add little plus, and we type ZinQ processing subsystem is shown. So this little block has some input, outputs. Great. I will press this plus here, type reset, and I want the processor system reset. Yes, this is the right one. Okay. So you see that there is a lot of input and output all over the place. What is good is Vivado knows that you're going a certain way, and it knows that you will use those two together. So you can run those automation tools that will do it for you. So I will run this. make sure this is connected. I say OK, and it will generate 2 outputs that I needed. Now, the connection, I want to connect stuff between those two. One connection, I select all, and it connects here. One of the things I need to do is connect this clock to the input of here, like this. Why? I must admit that I don't know. So it would be a good question to answer. Okay, so we save this, and we can now double click on ZenQ. And we will see that there is a lot of stuff in that. So for instance, we see our 2 ARM Cortex A9 here. We see a lot of peripheral input here. We see a central interconnect. One of the things that you need to know now is that all of those systems inside the FPGA uses what is called a AXI bus. It has three mode. For now, we will use them without knowing, but at some point, if we want to use, for instance, the HDMI port as output, you need to sorry, I forgot what I wanted to say. I just got distracted. Okay, yeah, sorry, I start over. So if you want to use the HDMI output, you will need to use the AXI stream protocol. If you want to communicate between one of your modules in the FPGA and the CPU, you will just use the straight AXI4, and there is a AXI4 Lite that gives simpler structure. In what you can imagine is that it uses less connection, so it works, but maybe not as fast as the AXI4 standard or the AXI stream. Great. So we see the RAM, we see the L2 cache, we see the R3 controller. There's a lot of things here. We can even see outputs here. Now what we want to do is to make sure that UART is open. We can see it here, but if we go over there, we have this setup here. So the concept of bank we see here. We won't touch this, but it by default is the right value, 3.3 volt in bank 0 and 1.8 for bank 1. I think bank 1 is connected to the DDR3, so it needs 1.8, and for a reason that I couldn't say why it used 3.3 on bank 0. So if I go down, I will see that UART 0 here was in fact connected. In fact, I just changed which one, and that is not good. I want to use, was it this one? I don't think it's on block 0. Wait a second. I was supposed to see right here. Oh yeah, maybe it's this one because we want to access through USB. That is 3.3. Okay, so everything is okay. So UART 0 should be okay there. Oh, we don't want modem signals. So this is one of the things we want to make sure is properly set up. Other things that we can look is clocking. We won't change anything for now, but we can create. Okay, first of all, we have our CPU clock. It's clocked at 650. You see, we can go up to 667. So in fact, maybe we can push it to that value, but for now, it's not needed really. And the DDR is clocked at 525. I can add up to three other clock on my setup. But you have to know that sometimes if I activate some of those clocks and change the value, let's say I want this one at 50, sometimes it can influence other clocks. So you have to be very aware. What I have understand is that one of the things that is very hard to handle in FPGA is clocks. So it exists, you can handle them, but it is something that requires experience. So for now, we don't have anything to do with it. Now, this section, DDR, we won't touch it. I think de facto, with when I selected Arty Z7 as the card I use, it already set the right timings everywhere. So what chip we use, what is activated, the number of bits per whatever, everything has been set up. The delay cycles that needs to be accounted for. But if you were to create your own FPGA, your onboard, you will probably use something like Altium or KiCad, and from those tools you will extract those values. Okay, so it can be important to know that it exists, and it is important. It might, if something doesn't work, you might need to look this in the future. Okay, one of the things I like is you can have access to a lot of documentation directly from the interface. I think if you don't download the when you install Vivado in Vitis, at some point it will ask you, do you want to have all the documentation, everything? I said yes. I think it adds a lot of space, like more almost 100 gigs of memory, not just for the documentation but everything. So you can have a lot of information on those documents, especially what I said, like how to handle the DR memory, and for instance, can I simulate this system? Because what you will do most of the time when you use stuff like FPGAs and stuff like that is testing. The goal is to test before sending it to fab if it has to be made in an IC. Okay, so that is something that is interesting. I think, like, if you use any of the blocks, usually if you over and press F1, I think it will open a little menu that will help you find information on that specific IP. Okay, so this IP, we don't have anything to do more than that. So what we've done is make sure UART 0 is activated. We look at the clock, everything seems okay. There's nothing much we can do for now. We don't have the knowledge anyway for changing this. We have the processor system reset that will handle the starting, the restarting of the CPUs, and there are some output that are connected to fixed IOs and DDR, which we won't very much using for now. Okay. So once we have this is the minimal element we need to have in order to communicate with the core, the CPUs. Okay, so we go back to source here, and we will click to our block design, right click, and then create HDL wrapper. So it will ask you, do you want to let Vivado manage wrapper? Usually say yes to that, but there is something you need to know. Vivado, Vitis, and all of the Xilinx architecture suite, okay, they are what I call a quantum system. It means that sometimes you tell it, hey, set this to that value and press apply, it falls into a superposition of it has been set as what you said or not. And at some point, you will click on generate, synthesize, whatever, and won't work because it will collapse in, oh, I didn't feel like doing what you asked me to do. So it can be very frustrating. So when something doesn't work, sometimes you will need to redo all of those steps. It's very annoying. It's very sad. For what I understand, Vivado use this here, this little Tickle console. Tickle is a language that is older than me, I think, and was used a little like Python back in the days, and is still used today on those projects. And if you use Tickle, it will always use as intended, but sometimes when you use the GUI, it doesn't work. It doesn't do the action, or it makes an error and doesn't go through, but sometimes you just don't see it, okay? So what you do, for now, we will use the GUI, but one of the things I want to try out more is the Tickle language. I mean, it's Tickle. I mean, it must be cool. Why wouldn't it be? I mean, it tickles. So create a digital wrapper. Let Vivado manage wrapper and auto update. Okay. So it will work a little. Considering what computer you have, it might be faster or slower. So now you will see in the source that the wrapper is different. So this is the blood design. It's like a orange-ish triple dots whatever here, but the wrapper is like a little blue dot with 3 dots at the side. So this, I think the 3 dots just said that this is the top module. Top module will be very important, especially when we will use VHDL files or Verilog. For now, it's just the main. Let's say that the top module is the module that is like the main in the C program. Okay, is the entry point. Good. Okay. So once this is done, okay, one of the things I forgot is that I could use this to rearrange the layout, but there's this little validate design that we can do before the wrapper. So I want to run it anyway. It doesn't really matter, but it helps find if there is error. For instance, there's a value that should supposed to be there, whatever, it will run it. Okay. So now what we will do is generate bitstream, and this operation can be a little long, so I will try to fill it with information, but hang tight. It will be important. So I click generate. I will. So you can use as many threads as you can. So I have a 16 core processor, so I can go up to 32 threads with my CPU. So but if you have, let's say, just 8, I think the max will be set to 16 anyway. So take as much as you can. It will try to use as much as it can. So, okay. So we let it run. And what will happen is that it will first run the synthesis. The synthesis will try, in fact, to define how many LUTs it needs, how the CLBs needs to be configured, etc. Then it will run the implementation. So it takes the synthesis, and the implementation is like, okay, now you start here and you try to do the circuit. It doesn't work. Now try here, etc. And once the implementation is done, now we generate the bitstream. The bitstream is the data that will be put in the flash memory we see earlier. that flash memory will reprogram the FPGA in the right way. So the application we try to do will run as intended. So when you use Vivado Vitis and you synthesize, you will see that in the right top right corner, there is some information that is displayed with a little loading icon. So that icon tells us that the bitstream is not finished yet. In fact, it didn't even finish the synthesis yet. So we have to wait. So the process, synthesize, implement, and debug. Sorry, not debug, but generate bitstream. And then there is another one we will do after that. There's like 5 steps that needs to be done in order to be able then to program in Vitis our program in C, so it does something. Okay, so that process is very tedious. I've read on Reddit there is like 3 or 4 weeks ago, someone complained like, why does it takes like 3-4 hours to synthesize my project in Vivado, sorry. And someone answered like C programmer complains when C program compiles in 8 hours. VHDL complains when it compiles in 20 hours. So there is like a 1 order of magnitude the difference between software development and hardware development. So it's very different. So our bitstream has been generated right now. It did it fast because the project is very small. I won't show the implementation. I can go here. You would like to? No. Look at this. Okay, remind me later. Maybe later. Okay. You can go there and you will see. No, not the. Sorry, here. The implementation is where you can have a lot of information on your utilization. Okay. One of the things I like to look is the report on utilization. It will say how many lots, how many CLBs, how many DSPs, whatever I use. I can even save those reports. So for now, I don't care. So if I go, why does the... Okay, it's already there, but it's timing. Sorry about that. I think project summary. No, it's not that one. Device. So this is our FPGA here. But why I don't see my summary? Okay. Power. So I have a lot of design runs. It's weird. Sorry about that, guys. It's usually when I click on utilization, it opens utilization. Oh, okay. I have to save it. Okay, sorry. So we look how many IO pad, like you remember earlier I said behind the FPGA there is like little balls. Those balls are connection to the FPGA. It can either be input, output. Those are configurable as one or the other, but there's also power and ground that are used. So for now we know that we use a 130 IO pads, 0, and we use one BU buffer. G I think it's I don't remember. The G stands for controller. So we use one of those, and if I go like slice logic, why does it want to show me? Maybe because I don't have any. Okay, here we see that we use the processing subsystem. So like I said earlier, there are blocks in the FPGA that are used to do specific jobs. They are not implemented in the CLB. The processing system, its reset is one. Processing system is one. The reset probably also. and block memory we talk about, and DSPs. So now this controller is something that activates the CPUs. Okay, so it seems that we don't use anything else. So that's pretty much the decision we have. If we had created our own entities or IPs, then we will have used lots, LUTs, block memory, etc. Okay? Perfect. So now I create the wrapper, then I generated the synthesis, generated the implementation, created the bitstream. Now I need to export here, hardware. It opens a new window that will create what is called a .xsa file, and that file will be used in VITSYS to so we will see what it does in VITSYS after that. Just for now, we need to create this. We need to create that Arduino platform. So we go next. Now we will need to change this. We will go to working software, select, and we will call it wrapper, like so. Next. So it says, okay, we create that. Cool. Finish. So again, I think this is pretty fast because we don't have much in the project. All right. So now, what's next? We start with this. And you remember earlier I said I have a problem with 2023. If I go to Tools, launch VITSYS IDE, it will not work. It will start VITSYS, but it will hang, and it won't. And even though VITSYS hangs, the Vivado will be blank. Like every single option will be grayed out. Everything here will be grayed out. Anything won't work. So what I do now as a workaround, I will start VITSYS. So sorry, it's on my main monitor, but I will start VITSYS 2023 manually. And if you install VITSYS and Vivado, don't make the mistake. There is two VITSYS. One is VITSYS 2023, and one is VITSYS HLS. HLS, say, it's something that you can write code in C and it would be transcompile in hardware definition language like VHDL. Okay, so once I started my VITSYS, I will need to open a workspace. Now what I do is open workspace, we go in C here, then we go in fact in working software, and I will create a no, I won't create anything, I will just use this. Select. So it's initializing. Alright. So now I will need to create what is called component. I will need two. One is a platform component and the other one is an application. So the platform component, it will be based on the XSA file I generated earlier from Vivado, and the application will be my software that will run and send messages through the UART protocol. So let's start with this. We will call it, like, just not to be confused, RT Fun Platform. Next. I think I go browse here, XSA here, open, next, and we wait. So we will use standalone, so no OSs, so bare metal, no tools at all. Okay, so it will be very bare bone. We will have access to what Xilinx gives us. It gives us a lot of tools, and PS7 Cortex A90 is the processor of our FPGA. Next. Blah, blah, blah. Everything seems okay. Finished. All right. Okay. So it's still working. Right. So we see our platform here. There will be a lot of source. Okay, C software. There will be a lot in here. So for instance, let's, I don't know why I don't see them. Okay, right here. So main.c, md5.h. There's a lot of stuff that Xilinx gives us. Okay. So what I can do is build this. Make sure it doesn't throw any error. Yeah, it works. The little green thingy. We are happy. Perfect. Now what we need to do. So all of this project does is you have to imagine that we define something in Vivado that activate a lot of components. All right, but all those components needs to be handled and needs to be initiated, needs to be configured, and all of this is done by this project. It's a C program, like a very low-level driver, if you will. So now we want to run our software that will send data through the UART that will use that platform. Okay, so what we do, we go here, create component. No, sorry, not no, it's just what I want to do is a where is embedded this one. I'm pretty sure this is the one. Okay, so we will Arty Fun app yet again in SW. And you see we have platform here. We select this one. Next. We will, there's nothing we need to change here. Next. Like a summary. Finished. So it will create our project. Great. So if I go here, source. One of the things we need to do, and it's very boring, again, it is, this has been explained in one of the Phil's lab video, like I said earlier, for a reason that I'm not sure why. We need to change this to RAM 0, all of this, and obviously there are no way to change them all at once, so we need to do it by hand. So I hope you enjoy looking at a man with a beard changing many RAM. Why does it work here? Little select inputs. Is this what everyone, isn't it what everyone wants in their life? Like just change them manually like this. Maybe I will say yes to the next well, the next survey for making Vivado Vitis better. That's a good example. I am having the time of my life. Patrick Sweezy. All right. Okay. So I think there's nothing more to say there. So new file, main.c. All right. So one other thing we will need is we will use xlprintf first. xlprintf will configure everything for us, all the UART, everything, and will be used a lot like printf. Okay, so instead of typing printf blah 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 blah, we say xlprintf blah blah blah. Okay, so it's very self-explanatory. So we need xlprintf. There's a problem now. It doesn't see the file. Sometimes it's make that error. Sometimes it works. So we will continue ignoring everything. So we will do our main file, and here what we will do is while one, we will do a xlprintf welcome friends. Okay, so we are on Windows. Respect, guys. /r/n, and that's it. And we will need uSleep, I think. And we do uSleep. Use this in micro. I think this is good. uSleep. Yes, he doesn't see it. Okay. But just for just to see if it doesn't really work, I will try to build this, and if it makes an error, we might need to do some modification. So we will wait. Okay, it failed. Problems. Is it .h? And if I retry, okay, if I clean, then retry, failed. Why? Problem. Okay, no, it doesn't work here. Why doesn't that? It doesn't work. Now it's time to have fun. Okay, let me look something quickly here. Okay, yeah. What is this? No. Oh, I remember that. I think I did this first. Let's try this. We will try again. We will call it Arty Fun sec. Next. C. Next. All right. What's the problem here? Okay. Next. Perfect. Finish. Let's wait. I think it has something to do with some linking that I don't know yet how to do. But here, what happens if I do this? It's fail again. Ah, yeah, because I don't have any file, I guess. The last time I think it did here. Where is the other one? Let's close this one. Okay. Doesn't see it yet. Okay. Yeah, same problem. Okay. So what was it? Is it that I took the hello world maybe? Let's try this one. Okay, we call it hello world for now. Next. So what you need to know is that I can have as many app projects as I want for the same platform. It doesn't really matter. I could use same platform for many applications. It doesn't. It's not, that is not a problem. But there is a problem in the way they create the um, the linking between all of the application. Okay, so if I go to the hello world here, there will be a hello world here. Okay, and we see platform. Oh, maybe it was that I used the so in the platform print successful cleanup. So what we will do, we will while true, we will just put this one here. We'll remove this. In fact, we won't have to clean up anyway. I will let it there. All right, so like this. I don't think I have another. Maybe this. We will try to run it without it for now. So okay, it builds. Perfect. Now we need to connect the FPGA and see if it works. So I forgot to get my wire. I think I have one here. Sorry. No, that is not the one. We will take like 2 minutes just to find the wire. I will be back. Okay, sorry about that. I will try this wire. I hope it's not only power. Let's get this here. I don't think I will have long. Maybe. We have to believe. So connect this here. Okay. Doesn't seem to be recognized. We will try to look here. No. Sorry. Where is Vivado? Here. Let's go. Open target. Here. sees it. All right. Great news. Okay. Just make sure that you see this. Okay, so I went back to Vivado, then click on Open Hardware. I clicked on, here was Open Target. So this is my FPGA. So we see ARM DAP0 and XC7-20. That is the FPGA. It says it's not programmed. That is the ARM, like both of the ARM CPUs. Okay, and that's pretty. It just says that it is connected. So now if I go here, I can click run, and by clicking run, I should have program the FPGA, program the software that will run on the CPU, and it should send hello world here at the speed of light. All right. So before we will open HTerm here, like so. We will put this like this. Okay, it's not pretty, but it's the best I can do for now. What we will do is make sure we use the right COM, and now I have like 1,000 COM signals. So we need to find which one. So I would try like the last one, maybe, I don't know, try to connect and hope when I push run that it will program everything. So it's programming, and we see all the other word that goes down here. So it was the right one. So now it's not really useful and beautiful. I don't think we will have time to do the like sending information. So the HTerm, I can like write something and send it in the terminal. But for now, the software I wrote here doesn't handle that. So what we need to do is for programming the next stream, we will code something that will echo back what we said. Okay. But if we want something to be a little more, I think is you sleep, just sleep. I don't remember the name. Just a second. We will ask to the Google. It's Xilinx. We want to know Vitis uSleep header file. All right. Okay, it's not that. Sometimes people have a way more complicated problem. Is it just sleep.h? Okay, let's try this. And I think now I can do sleep 1 second, but I think you sleep, yes, now I have u seconds or nanoseconds, so I can like, that is like 100 milliseconds, so I can remove this. So before I will just configure here like this. Oh, I inverted I did, that's not my code. Like this. Okay. So now we should see something more clean. So so you don't have to do this. I love to clean a lot, so to make sure there's no problem with my code. Like when you compile in C or C++ with any compiler, usually what happens is you make an incremental change on your binary. So sometimes it just doesn't work, and when you clean and rebuild, it just doesn't have any pollution kept. So sometimes it saves time, but sometimes it takes a lot more time. Sorry about that. The mute button. Okay, so we can see now that the data is still open. So if I scroll, you see that the hello world comes back. It's slower, so the sleep works, and we can communicate now. It's one way. The FPGA is sending data to my computer through the UART terminal. So next week we will have we will probably have time to complete this project, just to add the back and forth between me sending data and the FPGA answering back. That would be great, and we could probably tackle and have fun with some VHDL code and create like sample entity, a little bit more interesting than just AND gate. It will be a little bit more advanced, but it should be fun. So for I wish you a nice weekend, and see you next week. Bye now.